So today we will look at chapter 8. Excuse me. Chapter 8 talks about the area moments of inertia. Now, area moment of inertia is the next step in setting up to do stress calculations. So we found, what did we do last class? We found centroids, right? We found out where the center of a shape is. So now we're going to calculate, relative to that shape, some mechanical properties. So the area moment of inertia is a mathematical quantity that you cannot weigh or you cannot measure. You cannot observe it. It is abstract. But you do use that in equations to calculate the strength of beams and shafts for bending and buckling and twisting. Okay, the moment of inertia is annotated by the letter I. And it deals with the cross-sectional size and shape of a beam. So the moment of inertia, or I, is related to an axis, usually through the centroid of the shape. And it is the sum of products of the area times the distance square. And the distance is the distance to the centroid. So a moment of inertia about an axis, we'll call it x, equals the summation of individual areas times y distances squared. And if I were looking at a shape like this, here's my x centroid. The center or the centroid of the individuals is here. So let's see, I have a base and a height and a height and a base, even though it's one piece. And then my y distance would be this. This would be like area 1 and area 2. Not symmetrical part, so not that tough to figure out. If you were looking at the moment of inertia in the y direction, that would be the summation of areas times x squared. And then that would be going this way. So each area is multiplied by its moment arm, which is the distance to the centroid, giving what is called the first moment. Then again, multiply by the moment arm, and that would give the second moment and the area moment of inertia. The units on this would be inches to the fourth, or meters to the fourth, or millimeters to the fourth, whatever. But you can see that you have area, which is, you know, length and height, and inches, and then distance would be inches, multiply that all together. That's why you get a unit to the fourth. Because area equals base times height, right? So that is inches times inches. And then you're squaring the distance, so times the distance times the distance. And if those all have to be the same units, inches to the fourth. The value or the magnitude of the moment of inertia is the measure of a shape to resist bending. Okay, so the larger the value of I, the more it is going to resist bending. So if I take this yardstick, if I hold it up here, grab the end if you would please, and I push down, you can see that it's bending, right? But if we rotate it 90 degrees, it's pretty much not. With the same amount of force, it's not bending. So it's much more resistant to bending in this orientation than it is in this orientation. That's what we're trying to come up with a value for. Now, moment of inertia has nothing to do with the material, okay? It has to do with the shape of whatever it is. The material adds more properties to it to where we can calculate actual stresses and deflections of the piece. So the moment of inertia for that, if it were made out of aluminum or wood or marshmallows or steel, the moment of inertia for that shape, for that rectangle, the yardstick, is all exactly the same. So material independent. So if we were given a rectangular shape, it's 2 inches this way and it is 8 inches in height. The centroid is going to be exactly in the center of that, right? So that's going to be 4 inches. And I want to find my moment of inertia about the x-centroidal axes. So moment of inertia equals the summation of area times y distances squared. Our y distance is from the individual centroids to the overall centroid, and in each case that's 2 inches. So that is area, and they're exactly the same, top and bottom. So in this case we would simply multiply by 2. So the area, let's see, is 2 inches times 4 inches, and we're only doing half at a time. And the distance to the centroid is 2 inches. We square that. And let's see, area y squared. Oh, we have 2 of those shapes, so we have another 2 to multiply. And that equals 64 inches to the 4th. Does that make sense so far? Area. What if we take this same shape, 8 inches by 4 inches, there's our centroid. What if we decide to break each area up into a smaller area like this? Okay, so that we have a distance here and a distance here. Same on the bottom. This would be 3 inches, this would be 1 inch. And again, 2 by 2 by 2, I guess now, wouldn't it? So in that case, the moment of inertia would equal not squared, y squared. Same thing. So let's see our areas. Area 1 is 2 times 2. And let's see, the distance is 1. Plus area 2 is 2 times 2 times the distance squared, which is 3 in this case. And since we have a top half and a bottom half, we're going to take the whole thing and double it. So we'll multiply all of that by 2. And that equals 80 inches to the fourth. They're different, aren't they? Exact same shape, different. If we take this and look at the top half there and break it up into 1-inch pieces, do the same process. So we have a 1/2 inch, and then we have 1.5 inches, and then we have 2.5, we have 3.5 for our distances. I now equals, let's see, 2 times 0.5 squared plus 2. The areas are 2 because they're 2 inches wide, 1 inch tall. 1.5 squared plus 2 times 2.5 squared plus 2 times 3.5 squared. All of that times 2. And that equals 84 inches to the fourth. You can see the numbers are growing. The numbers are changing. The smaller the area, the more precise you get. This formula is very imprecise. It is very much an approximation. We really want to use smaller areas. So instead of breaking up these pieces into smaller areas, until you finally get a curve that levels off and there's very little change, right? You can do that with calculus. I suppose that's where these equations come from, calculus. There's actually an equation for a rectangle, and all the equations for the area or for a moment of inertia are in the back of your book. For this shape, I about the x-axis going through the centroid is equal to base times height cubed over 12. Now, if we apply that to the last thing we did, the base equal to the height equal 8. So we could say the 2 times 8 cubed divided by 12. The actual moment of inertia would be 85.33 inches to the fourth. So we're not going to break all of these little areas up into their individual components. We are going to use the equations that are provided us on the back cover of the book. Makes it a whole lot easier. You got a circle, you just look up the equation. You got a half circle, you look up the equation. Even easier, if it's structural steel, in all of those pages in the appendix, I believe 1 or something like that, all the moments of inertia are provided depending upon its orientation, of course. Just like the rectangle, an I-beam that's that way is going to be much stronger than an I-beam that's that way because it's taller. Okay, so and those moments of inertia are actually provided in the back of the book. So in this orientation, 85, right? If I laid this 8-inch piece down this way, it's now 4 inches by 8 inches, not 4 inches, it was 2 inches. It was 2 inches by 8 inches that way. This is now the base, that's the height. The base, so the moment of inertia would now be, let's see, 8 times 2 to the third divided by 12. And that equals 5.33 inches to the fourth. So while that's not a number that will actually provide strength, you can see by the example with the yardstick why it would bend in one direction and not the other, because it has a lot more inertia, a lot more moment of inertia, area moment of inertia, or resistance to bending in that other orientation, and the numbers go along with that. For a circle, pretend that's perfectly round, the moment of inertia is pi d to the 4 over 64, which reduces down pi r 4 over 4. For a triangle, the moment of inertia is base times height cubed over 36. I'm sorry?
Is there a base that's that shape, like on a bigger object, or?
It is for a cross-sectional area. Now there is another, so these are about the centroid, okay? These are about the centroid, and they're the ones that we'll use all the time. There is an equation in the back of the book that is about the base. For like a triangle, that would be BH3 over 12. So don't confuse that with a rectangle. And a rectangle about its base down here like this is BH3 over 3. But again, we're probably not going to use those. We'll do a couple of examples here. So, given a rectangular plate with a hole cut out in the plate at the centroid, let's see, I have a base of 4 and the height of 5. Diameter of the hole is 2. I'm going to call this area 1, and I'm going to call the whole area 2. And I'm going to find the moment of inertia about its x-centroidal axes. Now this is a composite, all right? We have one part and we have another part. It's a hole, so for the hole, just like we did for the centroids, we subtract. Moment of inertia for shape 1 is BH cubed over 12, and that is 4 times 5 cubed over 12. That is 41.667 inches to the 4th. Moment of inertia for shape 2, about its x, which actually would be the same as the y, is pi times the radius to the 4th over 4. And that equals pi times 1 over 4, which equals 0.7854 inches to the 4th. So moment of inertia for the entire part is 41.667 minus 0.7854, and that equals 40.88 inches to the 4th. Make sense? We're good so far? My pen is really acting weird. Given, let's see, I'm going to throw something up here, a little different, a little easier actually. So I have a W 8 by 13, and I'm going to call that shape number 1. And over here I have a half round that has a radius of 3 inches, and I'm going to call that shape number 2. And the half round is located exactly dead center, making them easy to start with. And I want to find the moment of inertia about the x-centroidal axes. First thing I do is I go to the back of the book, page 592. Make it simple on myself. I'm going to find that the moment of inertia for the W8 by 13 equals 39.6 inches to the fourth. Okay, so that's taking half the work right out of it. And that's for number one. Moment of inertia for the half round. Going to the back of the book. So you go to the back of the book, you look at the half round, and actually they show the half round in an orientation like this. Okay, and they say something along that for X and Y. Is that correct? So what do we have to do? We have to rotate that, don't we? And now what is the equation for X? It's not the X that's given in the back of the book, right? You have to rotate it 90 degrees. So that is 0.3927 r to the fourth. Is that what you see in the back? Everybody understand where I got that? You look at the equation and you make it apply to what we're working with. So 0.3927 times the radius, which is 3 to the power of 4, equals 31.8 inches to the fourth. Summing this up, equals 39.6 plus 31.8. And there's actually two of those, right? There's one on each side, so we could write 31.8 again, or we could multiply those by 2. And we get a 103.2 inches to the fourth. Moment of inertia for the entire part. Well, adding just a couple of little 3-inch half rounds in there, tripled the strength on that, didn't it? Well, tripled the resistance to bending. How's that?
So that's what those numerical values represent, the resistance to bend.
Yes. Bend, buckle, twist, yes.
So there's can't, since we're dealing with area things.
No. Well, if there's a hole in it, like with that one piece,
Yeah.
it would be a negative area, but when it's all said and done, it is a positive value because you hold the thing in your hand. It actually has a resistance to bending in your hand. It doesn't provide how much resistance, but that's what you do next.
So does that mean that you have to get out 103 inches before that will bend?
No, it doesn't mean that. No, not at all. It doesn't mean how much it bends. It doesn't mean how far you have to go this way or that way to do something with it. It is just a number that is plucked out of the air to put it in an equation that we'll worry about later. This is just a baby step working up
I
to...
was trying to figure out, okay, no, what does this mean? I mean, really?
What is it? Again, you have a steel bar or you have a wooden bar. They both have the same inertia or resistance to bending, but the material properties of the steel obviously enhance the bending resistance, right? Versus wood.
So if you did the calculations with including the material, the steel would have a higher value than the
What?
wood.
The steel would have a less value because when you do things, you're going to calculate stress, you're going to calculate deflections,
So
things like that. So
shape rather than
exactly, yes, shape, exactly. It's all about the shape. So what we've done so far is all about symmetrical pieces. What if you have something that is not symmetrical? Well, then you transfer the moment of inertia to another axis. So the transfer formula is I equals I of the individual object or the individual shape, I sub O, plus the area times the distance squared. And if you have multiples, you sum those up. So the summation of I sub O plus AD squared. You know, I1, I2, I3, A1, A2, A3, distance 1, distance 2, distance 3. So multiple shapes, multiple moments of inertia, multiple everything. As an example, let's say I have a 2x4 shape, and I have an axis down here that is 2 inches below my shape. There's the centroid of the actual part is right there. So remember that regular I is the moment of inertia. I sub O is the moment of inertia of the individual parts. Area is the object area. And the distance is the distance from the centroid of the individual to the axes that you want to transfer the distance to. So I'm given this part. I'm going to find the moment of inertia I'll even put some primes on there so that we can see that those are prime x's down below. So I know that the moment of inertia of the individual shape is base times height cubed over 12. And that equals 4 times 2 cubed over 12. And that is 2.66 inches to the fourth. The area is 2 times 4. And that is 8 inches squared. And the distance. And again, yeah, we're coming from here down to here. So I have the 2 inches there plus a 1 inch there. So my distance equals 3 inches. Now I can put that into the formula up here. So I equals I sub O 2.66 plus the area. Let's see, yes, that is 8 times the distance squared. .66 inches to the fourth. Now we know that moment of inertia I, the units are inches to the fourth. Area is inches squared. Distance is, well, inches, but then we square it, so it's inches squared. So the units work. We have to make sure that their units work. Let's see.
So in that case, we didn't have to sum anything because
There's only one bit. Yeah, you don't have to sum anything. Right. Have a diameter here of 2. Three inches above an x-axis. And I want to find the moment or of inertia at the x-axis. My solution, let's see. Moment of inertia of the individual shape is pi d fourth over 64. And let's see, so 1 to the fourth is still 1, and actually it turns out to be 0.7854. Let's see, I don't have area in my notes here, but we'll work at that. So total inertia is I sub O plus AD squared. 0.7854 plus the area, pi times the radius of 1 squared, times the distance squared, which is 3. Moment of inertia is 29.06 inches to the fourth. Just by moving it up and securing it gives it a lot more resistance to bending. Now, floating out in space really doesn't make much sense. And that's why we have what are called composite moments of inertia. Kind of like what we did with the I-beam, and we had the little half rounds welded at the middle, but often the world is not symmetrical. So various shapes are transferred. Like I said earlier, moment of inertia equals the summation of all the individuals plus the area times distance squared. So the moment of inertia is the sum of all moments transferred. And that might look something like, I1 plus A1 D1 squared plus I2 plus area 2 plus, not plus, times D2 squared plus I3 plus A3 D3 squared, and so on and so on. If you have a whole bunch of different shapes, you have to transfer a whole bunch of different things. So there's actually a process that you really need to worry about, and that is for whatever shape you're given. Let's say if we were given something that maybe looks like this, or something that maybe looks like this, or whatever. We talked about finding a centroid when we're looking at things like this. Break it up into its individual pieces, okay? This one could also be the box subtracting two triangles. So it's either a smaller rectangle adding two triangles, or it's a large rectangle subtracting two triangles. Whatever, however you want to do that. But the first thing you need to do is break it up into the individual composite areas. So one, break it up into simple areas. Number two, we need to find the centroid of our composite areas. And remember, finding the centroid was a bunch of steps in itself, right? Individuals, and then transfer them and do some calculation to determine what they are. Once you find the centroid, you need to calculate the distance for each shape to the centroid. Step number 4. Calculate the moments of inertia for the individual shapes. Step number 5. calculate the moment of inertia, which is again the summation of I sum O plus AD squared.
If we're finding the centroid of composite, why do we need to know the distance that each shape is centroid? Shouldn't just be one centroid defined? That we work on a composite?
Well, if we look at like this over here, we know that, and we know that. But the centroid is going to be somewhere in there. So we need to have it. We need to find the moment of inertia about this shape, and then calculate its distance. Find the moment of inertia, which I would assume be the same. Calculate that distance, and the moment of inertia for that shape, and find its distance. So they're all the distances is where we need to calculate the composite, and then all the individual.
Is there even a way that would be a little bit more efficient?
That is the most efficient way that there is.
You know what I'm saying, between selecting whether you're gonna do 3 separate lengths of boxes and 2 triangles, or...
A box and 2 triangles added, or a box and 2 triangles subtracted,
Yeah.
I think is kind of the same thing. It all depends on how you see it.
Okay.
It truly does.
But there isn't one that's more efficient.
I don't think so. But there might be an inefficiency we can talk about in a second, though. Okay? Let me do an example. Let's see. I have a box here. On top of a box here. This is 2 inches tall. This is 3 inches tall. It is 5 inches wide. And this is 3 inches wide.
Sitting on the ground?
Sure. Doesn't really matter, but that's sure.
You have floating in space. So, how is that?
What we want to do is we want to find the moment of inertia at the centroid. Okay, so it doesn't matter if it's sitting on the ground. Now I'm going to redraw it over here just to be a little, actually, you know what, it doesn't have to be quite that tall. That's a little disproportionate. There we go. So step number 1, break it down. So we have, let's see, we'll call this area 1 here, and this is area 2, or shape 1 and shape 2. Step number 2 is to find a centroid. Let's see, the centroid, you'll remember, y bar equals the summation of areas times their individual y distances to a known point divided by the total area. So area 1 equals 3 times 3. Area 2 equals, let's see, that was 5 by 2, so 5 times 2 equals 10. Total area equals 10 plus 9. So locating the centroid from the base, let's see. This is 1 inch here. And the center of that is 1.5 plus 2. So that should be about 3.5, right? So area 1, 9. And my distance, 3.5. area 2 is 10. My distance is 1, divided by the total area of 19. Y bar equals 2.18 inches. So 2.18 puts the centroid right about there. My distances now so this is distance 1, this is distance 2. So step number 3 is calculate all your distances. You see where I'm getting my distances from the individual centroid to the centroid of the composite. Distance 1 equals, let's see, going from the base and then back down to the centroid, it is 3.5 minus, let's see, the distance here, and that was 2.18. There we go. So 3.5, take away 2.18. That equals 1.3158. A little bit of overkill on precision, but that's okay. Distance 2 is, let's see, 2.18, because I have to go up and then back down to find that distance. And we're going to subtract the distance from the centroid to the ground, so we're taking 1 away. Did everybody see where I get the distances? Step number 4. Moments of inertia for the individuals. So shape number 1 is base times height cubed over 12. The base is 3. The height is 3. Divided by 12. Cube that, divided by 12. And that equals 6.75 inches to the 4th. The other one, base is 5 inches. The height is 2 inches. Cubed divided by 12, running out of room down the bottom. And that equals 3.3 inches to the 4th. Step number 5, calculate our composite. And remember, that is I equals the summation of I sub O plus area times distance squared. Let's see. Yeah, I'll go ahead and write it out this time. So that is I1 plus A1 D1 squared plus I2 plus A2 D2 squared. So a moment of inertia 1, let's see, right here, 6.75 plus area 1, 9, times distance 1, 1.3158 squared, plus area, or moment of inertia 2, sorry, 3.3, plus, let's see, area 2 is 10, and distance 2 is 1.18 squared. Moment of inertia equals 39.68 inches to the 4th. Now, as a check, you can draw this in AutoCAD, turn it into a region, and do mass prop. And this checks good in CAD. Okay, you can't use that for your answer, but you can check your answer. So if you have a problem and you're not sure what the answer is, maybe you don't have an answer to the back of the book, whatever, or out in the real world. I actually had a guy where I worked He didn't use CAD, but he was a professional engineer. He had his PE stamp. And instead of doing some really weird calculations, setting up some really complex beams, he'd say, will you give me the moment of inertia of that? Because I know you can draw it real quick. So I just draw it real quick, do mass prop, give him a number back in a matter of minutes versus hours for him to do the hand calculations. So it does work. AutoCAD does do a real good job about calculating mass properties. What's that? I just told you. Region, mass prop, done. And actually, we have already done that in CAD class. You may not remember. I think we did that in the second or third day. Let's see. I'm going to step it up here. I want to get this one done as an example. It's not so bad. And then if we have time, I'll come back and do one more example. But there are some homework that is assigned that actually uses structural steel. So I want to make sure you see at least one example using structural steel for a composite beam. Pretend that's a nice straight channel. And this is a C10 by 15. And this is a 1" by 4" plate steel. This is shape number 1. This is shape number 2. Okay. Now I want to find the moment of inertia at the centroidal axes. Let's see. Fortunately, we can go to the back of the book and look up everything we needed to know about that channel. So step number 1, I'll use this area up here. So area 1 equals, let's see, I'm not sure what page that is. Anybody have a page number? 595, that sounds about right. So I get area 1 of being 4.49. Moment of inertia for this shape is 2.28. Now there are some other things that we need to worry about. One of those is the thickness of the web, because the way this thing is built, we have that, and then we have this other piece underneath it. We need to know what the thickness of the web is so that we can calculate where the distance to the centroid is of the channel relative to the ground or to the base. Okay, so we need to know the thickness of the web on this. So thickness of the web is 0.240. And actually the y-bar, this distance here, is 0.634. But now calculating, I'm going to erase this little bar right there because that's just the y of the individual piece. The y bar to the ground for this is actually 4 inches plus the thickness of the web, 0.24, minus the location dropping back down of 0.634. So the actual y-bar distance is 0.3606. Area 2 is 1 times 4. Let's see. I2 is yeah, I guess I don't need to worry about that right now. We'll come back to I2. But we do care about the height of that, where the centroid of that individual piece is right there, and that's half the height. So y2 equals 2. Now finding y-bar for the composite shape, which again is a summation of area times y distance over the total area. Nope, I didn't do a total area over here. Area equals 4 plus 4.49, and that is 8.49. Area 1, 4.49 times the distance. That's 3.606. There we go. Plus area 2 of 4 times the distance of 2 divided by 8.49 equals 2.8493. So right there is x, and I need to find the distance here. That should be distance 2, and distance 1 should be here. So step number 2, finding my distances. Distance 1 equals 3606 minus 2.849. That equals 0.7567 inches. Distance 2 equals 2.849 minus 2 inches. That is 0.849 inches. Step number 3, moments of inertia. Now I already have I1 is 2.28 inches to the 4th. Moment of inertia 2 equals base times height cubed over 12, and that is base of 1 times 4 cubed over 12, and that is 5.33 inches to the 4th. Next thing, I need to calculate I, and that is the summation of I sub O plus AD squared. And this is I1 2.28 plus A1 4.49 times the distance 1, there we go, 0.7567 squared, plus I2 5.33 plus A2 4 times the distance 2, 0.849 squared. I equals 13.1 inches to the 4th. Now, it was asked earlier if there might be an easier way to do some of these things. Now, this problem, you had the issue of the thickness of the web and finding the distances to the ground here, because you had to add in the thickness of the web and then come back down and do. Maybe, just maybe, it would be easier to tip this whole thing upside down and do your calculations this way. Okay? Sometimes it is easier to do that. It truly is. And I don't think I'm going to run through those, but it turns out that the distance 1 and distance 2 are exactly the same. The moments of inertia are obviously the same because they're the same shapes. You simply flip them over. You didn't change their orientation. You just reversed. So because distance 1 and distance 2 are the same, you get exactly the same numbers. It just might be a little bit easier to calculate this distance here because it's the thickness of a web plus 2 versus doing all the other stuff. And then the other one is already exactly what it was, 0.6, whatever that was. Okay, so those distances, they fall out just a little bit easier. We have a shape. So there's a nice shape. This is a hole, 1-inch diameter hole. And I want to find the moment of inertia at the neutral axis. Which is also the centroid. Sometimes the book might throw a little bit of different terminology, and that's what we're talking about. So the moment of inertia at the neutral axis. First thing I want to do is to break this thing down into its individual shapes. So I have this 1-inch by 3-inch piece here. I have a triangle over here. Let's see. Looks like that. And then underneath it I have another rectangle. And in the center of that rectangle I have a hole. We'll call this shape 1. This is 2. This is 3. And the hole is 4. Doing a little bit of math here. Let's see the center of both of these pieces. Let's see, that was 2 inches. So that's 1 inch. Let's see, we have the center here and the center here. That's 3 inches tall. The centroid of a triangle is 1/3 the height. So 1/3 the height is 3. So that is 1 inch plus the 2 inches. That gives an overall location of 3 inches there. And then this is 3 inches tall, so that's 1.5 plus 2. So that's at 3.5 inches. Area 1, base times height. 1 times 3. Area 2, base times height over 2, right? And the base is 2, the height is 3, divided by 2, those drop out, that is 3. Area 3, it's a rectangle, 2 by 3. So 2 times 3 is 6 inches, and area 4 is pi r squared. .14 times 0.5 squared, and that equals 0.7854. Total area is 3 plus 3 plus 6 minus 0.7854. That equals 11.21. Finding y bar. A1 y1 plus A2 y2 plus A3 y3 minus A4 y4. 3 times 3.5 plus 3 times 3 plus 6 times 1 minus 0.7854 times 1. Y bar divided by the total area, 11.21. Y bar equals 2.2038. That puts y bar right about here. So let's see, my distance 1, distance 2, distance 3 and 4. Calculating my distances. Distance 1 equals 3.5 minus 2.209 blah blah blah, which equals 1.296. Distance 2 equals 3 minus 2.2, and that is 0.7962. Distance 3 equals distance 4, which is 2.2 minus 1, 1.2038. Moments of inertia. Shape number 1, BH3 over 12. One times 3 cubed over 12 equals 2.25. Moment of inertia shape 2. That is BH cubed over 36. And that is 2 times 3 cubed over 36, which equals 1.5. Moment of inertia 3. BH3 over 12, the base is 3, the height is 2, and that is 2. Moment of inertia 4, pi r4 divided by 4, 3.14159 times 0.5 to the 4th over 4. And that is 0.0491. So now our total moment of inertia. Remember, I equals the summation of I sub O plus AD squared. So I1, 2.25 plus A1, 3, D1, 1.296 squared plus I2, 1.5 plus A2, 3 times D2, 0.7962 squared plus I3, 2 plus, let's see, A3, 6 times D3 which squared, which is 1.2038 minus I4 0.0491 plus A4, let's see, A4, there it is, 0.7854 times the distance squared, 0.12, or 1.2, sorry. Pretend that's all one thing. I equals 20.1998 inches to the fourth. Perhaps I should have written smaller.
5.4.
What's that?
The number in the big parentheses, it's after 0.7854.
121, distance 3, right here. Or distance 4, sorry, same thing.